Okay, welcome back. Today we're going to be working on section 4.2, talking about the natural exponential function. But before we do that, I have a few problems here for you to try as a startup. So pause this and try the startup problems and then check your work. Okay, on the first one, if you're going to put it in this exponential form here and passing through this particular point, then this is going to be my x and this will be my f of x. So I'm going to put the f of x in here and I'm going to substitute the 3 for the x. I'll need to take the cube root of both sides and then I get a equals 5. And so from there, I'll have f of x equals 5 to the x. As far as the domain range and asymptotes here, this is just a basic exponential function. If you recall, the domain of all exponential functions is negative infinity to positive infinity. The range is 0 to positive infinity unless we've had some kind of vertical shift, which we have not here. And the horizontal asymptote is at y equals 0, again, unless we've had some kind of vertical shift. So this is just a graph here, and you can clearly see the domain goes from negative infinity to positive infinity. Even though it looks like it's going straight up and never goes over here, if you were to go high enough, it would actually go out and up. So it's not going straight up, it's going slightly out and up. And as far as the asymptote, it's across here at 0. So it doesn't actually touch that asymptote, it just gets really close to it. Okay, number 3, this one was compound interest, compounded quarterly, so we'll substitute 4 in the place for the n, convert this to a decimal, and plug that in, and you should get this as your answer. For the annual percentage yield, the APY, that's, if you remember, your formula for the APY is 1 plus r over n to the nth minus 1. And so that's what we've done. We've got the 1 plus r over n to the nth, subtract 1 from it, and we get here that our APY is going to be 4.07%. Okay, so like I said, section 4.2, we're going to be talking about the natural exponential function. Okay, before we can get into that, I need to introduce you to a special number, and that special number here is e. This is actually the base of this special natural exponential function, and it is an irrational number just like pi is. So most of you are very familiar with pi. Pi is 3.147. It goes on forever. There is no end to it, and so we kind of contain all of those decimals in this one symbol here. That's the same thing for E. E is an irrational number. 2.718 is usually the approximation we use for it, but it goes on forever. And so we capture all those decimals by just using this number here. It is a special key on your calculator. It's used so often. Okay, so if we look at this, the number E is defined as the value that this expression approaches as n becomes large. So for those of you that have had maybe a little bit of calculus, essentially what we're saying is the limit as n goes to infinity of 1 plus 1 over n to the nth is going to equal E. So if we look at this expression as n gets larger and larger, it's going to get closer and closer to that value E that we talked about. So here as n's getting larger, you can see that this being evaluated at that value gives us a value that's pretty close to E that we defined earlier. Okay, so our natural exponential function, you're going to see it looks like this. So we've already looked at just kind of generic exponential functions where a can be anything. Well, we use this natural exponential function so often that sometimes we just refer to it as the exponential function. And it's just using a base of e, which is the 2.718, instead of this base of a. The e, which we said was 2.718, excuse me, falls between 2 and 3. And therefore it would be a growth equation, and you can kind of see how it fits between an exponential function with a base of 2 and an exponential function with a base of 3. Okay, as far as evaluating this, if you'll look on your calculator, you do have an E button that you're going to use, and you'll find that by doing second and the LN key. So the LN key is to the left of the number 4, And that's how you'll evaluate these. So on the first one, if we do e to the third, you should get this. So you can just check that and make sure. And then this one should be 1.177. And then finally, the last one should be 121.5 and so forth. Just be careful on WebAssign that you are watching how many decimal places it's asking for, because it is rather picky about making sure you do give the right number of decimal places. Okay, so here's an exponential function. So an infectious disease begins to spread in a small city of population 10,000. After T days, the number of people who have succumbed to the virus is modeled by the function. So here's the function here. How many infected people are there initially? So anytime we talk about something initially, that's an indication that we're going to use t equals 0. So we're going to take this expression here and plug 0 into it. Okay, so we're going to have 10,000 over 5 plus 1245. Anything to the 0, which this would all become 0, is just 1. So we're going to have 10,000 divided by 1250, and that's going to give us 8. So 8 people were initially infected by this particular disease. Okay, find the number of people infected after 1 day, which would be t equals 1, because t is defined in terms of days. So always be careful with time that you're making sure it has the right units. But this would be t equals 1 at t equals 2, and then again at t equals 5. Okay, so for t equals 1, t of 1 is going to be 10,000 over 5 plus Okay, we're going to put all that in our calculator, and we get 20.967. Again, depending on how many places you want to round it to. So basically 21 people would have it after 1 day. Okay, if we look at this for 2 days, we're going to do the same thing. So we're going to plug 2 in. So we'll have 10,000 divided by 5 plus 1245 e to the negative 0.97 times 2, and we'll get 54.37 for our answer there. And then if we do the same thing for 5 days, we'll have 678.13. So we did it down here, but we didn't on the other parts. This one would be 54. And this one's going to be 678. Okay, we want to graph the function. So if we graph this, we're going to end up with a graph that looks like this from the calculator. Notice that the window is very different here, because if you just graph the regular window, you're not going to see very much of this particular graph. So you may need to adjust your window in order to be able to see that. So when we look at these graphs, a lot of times it's really important to know where it levels off at. Like for instance, even during this pandemic that we're in the middle of with COVID-19, at some point we'll reach a saturation level where the enough people have it that it's not continuing to be transmitted at the same rate, and it's going to slow down. So we don't know what that leveling off is going to be. But if we look at this particular example on our calculator, we can actually determine that. So I'm going to go to the calculator. So over on the calculator, the first thing we want to do is to enter our equation. So I'm going to enter the 10,000 and divide that by, and I'm going to group the denominator with a parenthesis. So I'm going to have 5 plus 1, 2, 4, 5, And then I'm going to get my E by doing second and ln. So E raised to the negative 0.97. And then we're going to use an X for our variable. Okay, so from here we're going to graph this. And my window is not set for standard, so I'm going to go and do standard. Okay, when I look at this, I can just see the growth part. I can't see the leveling off. And if you remember yesterday or in the last class, we talked about COVID and how the New York model had leveled off. So we're kind of looking for that leveling off here, and we obviously don't see that. So what I'm going to do is I'm going to go in and I'm going to adjust the window. And just because I kind of know what I'm looking for here, I'm actually going to go up to about 3,000 on my Y max. And for my X max, I'm going to go out to about 100 and look at this graph. Okay, so sometimes you have to play around with that a little bit. You're not necessarily going to know where that happens at. So if I look at this and use my trace key and trace over, then what you can see is, I'm going to go back. Okay, so here we have, I'm going to start over here at the origin. Okay, so I'm starting at the origin, and you can kind of watch what happens with the Y as I go up. You can see that this Y is getting larger and larger until it gets to a certain value, and that certain value that it's getting closer and closer to is 2,000. So your calculator may not actually ever get up to 2,000, but it's getting closer and closer to that. So based on different factors, it appears using this model that about 2,000 people is going to be the maximum that it's going to kind of level off at that point, and it's not going to keep growing once 2,000 people have that particular virus there. Another way to see that is to go to the table. So if we go to second and table set, I'm going to start my table at 0, and I'm actually going to go up by tens this time so we can grow it a little bit faster. So I'm going to go over to the table, and you can see that here I start out at 0.8. That was that initial quantity that we found. And then when I go down here, I can quickly see that I'm already up about 2,000, and that's about as many people as will get that particular virus or disease there. Okay, I have one for you to practice with that's very similar to the one that we just completed. So try pausing the video and practicing with this one, and then check in your work. Okay, on the first part, how much salt is in the barrel after 5 minutes, we notice that it is measured in minutes, so we're just going to plug 5 directly into this equation that we have. And when we plug it in, we get 2.719 pounds for our answer there. How much is in the barrel after 10 minutes? That's just plugging 10 into that equation, and you get 4.945. Drawing the graph, if you draw the graph on the standard window, it's going to look like this, which looks a lot like a line. We know it's exponential, and so we want to widen our window out so that we can see where it's going to flatten out at. Okay, so as far as D says, use the graph from part C to determine the value that the amount of salt in the barrel approaches as T becomes large. So what I've done is I've just done some screenshots here rather than going back to the calculator. If I start my table at 0 and go up, you can see that it's getting larger and larger here. If I want to change my table set so that it goes faster, I could change that to 10 or 50 or whatever, and you can see as the X is going up, then this is getting closer and closer to and eventually leveling off at 15. I could find that same thing out by looking at my graph and tracing over. So it turns out that 15 is the value for Y that it's going to approach as X gets larger and larger. Okay, so is that what we would expect? Yes, it is, because the barrel holds 50 gallons. So with a 0.3 pound per gallon concentration, then 50 times 0.3 gives me 15 pounds of salt, and that's what it levels off at with that problem. So we're told that the salt has a concentration of 0.3 pounds per gallon, so that's where that 0.3 is coming from. Okay, continuously compounded interest. Sometimes we want to work with something that's compounded indefinitely and infinitely many times, and therefore we're going to work with continuously compounded interest. So with continuously compounded interest, this is our formula that we're going to be using. Sometimes we refer to it as the PERT formula, P-E-R-T. The A of T is still the amount after T years. P is still principal. E we know is that special number. R is the interest rate as a decimal again, and T is the number of years. Okay, if we look at this example, find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year, compounded continuously. So because it's continuously, we're going to use this formula here. So the amount after 3 years is going to be my principal, which is 1,000. E, my rate is 0.12, and we're going to multiply that by 3 years. We're going to get 1,433.33 as my answer. All right, here's one for you to have a chance to try. Okay, again, this one is continuously, so we're going to have A of 4. This time we're looking at 4 years. Our investment is $2,000. My rate is 0.035, and my time we said was 4 years. So when I plug that in, we get 2,300.55. So $2,300.55. Okay, that concludes section 2 in chapter 4. Please let me know if you have any questions, and have a good day.